Chapter 6 of the Functional Programming tutorial. It is about computations in a filterable functor. Consider this example. This is a mathematical computation. How would we express this computation in functional program? We can write this Scala code. Now, let us look a little bit more carefully about what this computation is doing. For all integer x such that x is between 0 and 100, we select those that have positive value of cosine x, and then we compute square root of cosine x and sum over all those. So we sum over only those that have cosine x greater than 0, those x, and then if cosine x is greater than 0, it is safe to compute the square root of cosine x. So we compute that and we add together all those values of the square root of cosine x. So in the Scala code, this is represented by this program, which is we take the sequence from 0 to 100. We map with a cosine function. We filter with the condition that the argument is greater than 0. After the filter, only those elements which are already transformed to the cosine values are left. Then it is safe to take the square root of those cosine values and add them up. So this would be approximately the result. Now, Scala has a different syntax for computations like this, where you have a chain of map, filter, map, and so on. This syntax uses the keywords for and yield. So it is sometimes called a for yield syntax. I prefer to call it a functor block because this does not work unless you have some functor type around, and you're using this only for computations in a functor type. Other names for this syntax are for comprehension. Now, this comes from Python, I believe, and it does not add to my comprehension of what this code is doing, so I will not call it a for comprehension. I will call it a functor block, because it's a block of code for something, yield something, and it has to be handled as a single expression. So if I want to do anything with this expression, I have to put it in parentheses, like this. So it's a block that is an expression. It yields a value. So how does it work? We can compare it side by side with the code of this program written a little bit more verbosely, where I wrote out all the arguments with names. So here I say, for example, cosine of underscore, and this is the Scala syntax for a function like this. X goes to cosine of x. So Scala allows you to have this function shorter. Just say cosine of underscore. But let's write it out with names of variables. Then it will be map of x going to math.cosine x. Then filter y is going to y greater than 0. Then map y is going to square root of y, and then sum. The for yield syntax describes exactly the same computation, and we can compare line by line how the syntax is changing. The for yield syntax is automatically transformed by the compiler into the form on the right. So this is just syntax. There is no special keyword or function that is called yield. There's a keyword yield, but yield itself is not a function. It is a syntax keyword. So all of this is removed by the compiler and replaced by the code on the right. The first line is equivalent to saying that whatever follows will have the value x going from 0 to 100. The first line in the for yield block must be this line with the left pointing arrow. To the right of the left pointing arrow there must be a functor value. So this value is the sequence from 0 to 100, and as we know, sequences are functors. To the left of the arrow is a variable, or more generally a pattern with pattern variables. In these examples we will only use simple variables to the left of the arrow, but it can be a pattern match. So the first line says take x to be any value in this sequence. The second line says compute cosine of this value and call it y. Exactly similar to this is that we compute the cosine of x, and in the next whatever comes, filter or map or whatever, we call that y. We're free to call that x here, in fact, aren't we? It's a different scope. It would be confusing, however, if we wrote x here, x equals math.cosine of x. We can though. It will be valid. It will be just confusing. So let's not do it. But it would be exactly the same code if we renamed y to x in what follows in this block. Just because it's translated into this kind of code, and there we're free to call this variable by any name we want. We can call it x, y, or whatever. The next line here says if y greater than 0. Now if is a keyword, and this is an expression that should evaluate to Boolean. Just like here, this is an expression that should evaluate to Boolean, and this is under filter. The last line is yield, and after yield there can be some expression. This expression is what comes here after we do the last map. So actually yield is just as part of a block as all this stuff. It is not different. We could put this computation inside the block. For example, we could have said z equals square root of y and then say yield z instead of this. It would be exactly the same computation. This would be here the last map. After that we do the sum. Now the sum cannot be done inside the functor block because it takes us out of the functor context, as I say. Sum transforms a functor value, or sequence in this case, into a single number. So every line in the functor block after the first line will be repeated for every x that belongs to this sequence. However, if some y in this computation is non-positive, we will not compute the square root of y. So this value will be omitted from this resulting sequence. Just like it is here, because it's the same code, it's just written in a different syntax. After we filter, only values that pass the condition are left in the sequence. So the same logic is a little more visual in the functor block syntax, that anything after the if only is executed or is computed when it passes the condition. So, to summarize, the functor block is a syntax for manipulating data within a container, where this container, in this case this was a sequence of integers. It could be any container, which is a functor, which is any type constructor that has a map function such that the functor laws hold. As a result of computations in a functor block, we manipulate data inside the functor or the container. However the data changes, it will still remain within the same container. So the value of this expression is a sequence. It can be a sequence of double numbers, double precision floating point numbers, as it is in this example. So it changes type. The data items inside the container can change their type, of course. The container does not change. It is still a sequence. We cannot change the type of the container in the functor block. It must be within the same container. So, in chapter 4, we have started with the container semantics, looking at the map function, and generalized from it to obtain the concept of a functor. We will do the same in this tutorial to generalize the filter. We will find what laws the filter must satisfy and what kind of containers will be such that you can define a filter method. Now, more precisely, in Scala, there is a method called withFilter. If your functor has a method called withFilter, then you can use this functor in a functor block with an if keyword. Otherwise, it will fail to compile. So we will call a functor filterable if it has a method called withFilter that satisfies the appropriate laws that we will investigate later in this tutorial. However, for convenience, many functors also define the filter method. It is shorter to write. It might be implemented differently for performance reasons. In this tutorial, we will not distinguish between filter and withFilter. We will consider them to be the same function. Their types are exactly the same, and they are isomorphic in the sense that they yield maybe different implementations, but these implementations are completely equivalent. This is the type signature of the function withFilter that needs to be implemented in order for us to be able to use the if syntax in a functor block with the functor f. Scala syntax will be available no matter how you define this method withFilter. It must be that you are able to write f.withFilter. It can be done using an implicit conversion, a type class, or just defining a method withFilter on your data type. That does not matter. You can use it in the functor block after that. So the main questions that remain for this tutorial is, what are the required laws that capture the intuition we have for these computations? And once we found those laws, what are the possible data types that are filterable? The main intuition is that the filter call, the function filter, when you call it with some non-trivial condition, may decrease the number of data items that a container holds. It may not decrease it, but it may also decrease. The container, therefore, must be able to hold fewer or more data items. It must be able to hold, in some sense, a different number of data items. Of course, still of the same type T. So here's an example that we are familiar with, which is option. The option type, it is written in the type in the short type notation as 1 plus t. And here are some computations that we can do with an option using filter. If an option is empty, then whatever you filter it or whatever, it still returns empty, so that's not very interesting. But you see, if this number passes the condition, then the number remains. But if it does not pass the condition, the option becomes empty. Also, you can use with filter on an option that actually returns a different type, not option, but that type is isomorphic to option. So it still has all the same methods as the option has. It has map, it also has filter and with filter and so on. So it's isomorphic, and it can be used if you wish, but as I said, in this tutorial, it will be not important for us how this is implemented and what types are behind this operation in a standard library. A standard library makes its choices, which may change with time. What's important is that the results of filtering can be an empty option if the number inside the option does not pass the condition. The second example, familiar to us, is list. So a list type can be visualized as this short notation. So this is a disjunction of unit, a single data item of type T, 2 data items, 3 data items, and so on. And if you apply filter to a list, then only those elements that pass the condition remain in the list. How does it work? So for instance, a list 10, 20, 30 is a disjunction of 3 elements, which is this part of the disjunction. After the filter, only 2 elements remain, 20 and 30. So after the filter, we are in this part of the disjunction. In the second example, after the filter, we go from this part of the disjunction to this one, the empty list. So what do we learn by looking at these examples? It looks like the data type must be a disjunction of some sort, or must contain a disjunction maybe somewhere. And this disjunction must have a different number of data items of type T, so that when some data items do not pass the condition, we take data from one part of the disjunction and put it into another part of the disjunction. So for example, here we had 10, 20, 30. Now this one did not pass the condition. We still had these 2, so we put them into these 2 data items in this part of the disjunction. So the data goes from one part of the disjunction to another as necessary, according to whether the predicate P returns, which is this predicate P, the function from A to Boolean, or from, in this case, it will be from T to Boolean. Whether this predicate returns false on some T values or true on the values that you actually have in your functor. Another curious thing here we can notice is that when some data item does not pass the condition, like this one in this example, we can see what's happening as if we replace this T with a unit, with 1, with a unit type. and the result would be 1 times t, which is isomorphic to t times t. So 1 times t is this part of the disjunction, actually. So this is a curious phenomenon that we notice at the type level, that certain items are replaced by a unit type, and then the resulting type, like this, for example, would be t times 1 times t. It's equivalent to t times t, and that's another part of the disjunction. So we can accommodate replacing some items t by unit type. That does not break the type. It still remains within the same disjunction. We will use this intuition later in the second part of this tutorial. And finally, we notice that the container can actually become empty. So all of these examples contain a disjunction part, which is unit, which represents an empty container. Now, of course, there are names for this in Scala. So this is not the unit itself. It's in this case, it's a case object called none. In this case, it's a case object called nil, I believe. But that's just syntax. This is a name for a unit type. So Scala can have any number of named unit types. The unit is the standard one, but you can define any number of your own, of course. So these are these intuitions we gather from these examples. We would like to generalize this. To generalize, we need more examples. So let's consider a business application where we have the following logic. An order can be placed on Tuesday and/or on Friday. And under certain conditions, an order is approved. So separately on Tuesday and on Friday, the order is considered for approval. Now this logic of approving or not approving is a function such as amount less than 1,000 or any other requirements. We would like to abstract away the logic of approval from the logic of which orders are approved. And that logic is the one that the filter function represents. So therefore, we will also abstract the type of order to a type parameter. So we will consider a class or a data type orders with type parameter A, and it has two parts as a conjunction. One is an option of A, another is also an option of A, representing that we can place an order on Tuesday or not, and we can also place an order on Friday or not. And then we define a filter function on this case class by simply calling the filter function on each option. Now the filter function on option does what we just saw. It does these things. So that's going to represent exactly what we want. When P is given, some kind of approval condition, we can apply this condition to the order placed on Tuesday, if any order was placed on Tuesday, and also we will apply it to an order placed on Friday, if any. The result of this definition is like this. So suppose we placed an order for 500 on Tuesday and for 2,000 on Friday, but approval happens only when it's less than 1,000. So then the Friday order will not be approved and the Tuesday order will be approved. So the result will be this data. So what have we achieved? Well, we separated the logic of which orders will be approved from the logic of how orders are approved, and also from the specific data type that represents orders. So this code only represents the logic of how orders will be removed from our container, and that's what filter represents. Let's look at the example code. So this is this code. I have written here orders 1 because we will have some variations on it shortly. And here are some typical examples. So if we filter with this condition, then only this one survives. Now, of course, if no order was placed, then it's still empty on Friday. So if the condition is such that every order passes, then both of the orders remain in the container. And finally, when none of the orders pass the filter, then the container becomes empty. So we see that orders 1 is a container that can represent empty or non-empty sets of orders, and that's the logic we want. Now, in the short notation, this functors type is written like this. It's just a product of two option values, and option is 1 plus a. So it's 1 plus a times 1 plus a. As in the other examples, we see that the a is replaced by 1, or by the non-named unit, when the value here does not pass the filter. In this case, filtering is applied independently to both parts of the product. But we could consider other options. For example, both orders must be approved, or else no orders can be placed at all. That could be a business requirement. Another business requirement that one could come up with is that if at least one of the orders is approved, then both orders can be placed. So let's see how that works in code. If we implement the rule A, it means that both orders must be approved for them to be placed. Now, if there's one order, then this rule does not modify our previous behavior. If there's only one order placed, then we still apply a filter to it as before. But if there are two orders placed, then both of them must be approved. So let's see how this logic can be implemented. So first, we find what will be the ordinary filtering procedure. So the Tuesday orders after filtering is this new Tuesday and new Friday. Now the ordinary filtering procedure would be applicable if both of them passed the test, passed the predicate. Now this condition expresses that either the Tuesday is empty, and for the empty option, for all is always true. Well, this is a mathematical convention that empty for all is true. If this is not empty, then predicate must hold for the value of the option. So this condition, therefore, will be true either if both orders are present and pass the test, or if one of the orders or both are empty, and if not empty, they pass the test. So only in this situation we return something that could be non-empty. In other cases, we return empty container. So this expresses the business rule A. So for example, if we have 500 and 2000 and the filter is less than 1000, then one of them passes and the other one does not pass, and then we return empty container. So this is the new business requirement. In all other cases, we do exactly as before. So for example, here, one of them passes, the other was not placed, so that's fine. All of the orders that were placed pass. That's the business rule. And that's the result then. And finally, when both pass, then we return both non-empty. So this is the new rule. Now, the second business rule that we could consider, the business rule B, is that both orders are approved if at least one of them is approved. So both orders can be placed if at least one of them is approved. And so this is expressed by this condition. Exists on an option means that the option is not empty and its contents pass the test. So P is a predicate. Exists on an option is this. Means that there exists a value inside the option and such that P on that value returns true. So if at least one of them exists, so in other words, it's placed in order that was approved, then we return this, which is the value of the container unmodified. So we do not actually filter. So even if some of them did not pass the filter, so the first one did not pass the filter, here's an example. The first one passed the filter, the second one did not pass the filter. But the result is still that we return both orders. So both orders can be placed if at least one of them was approved. That's the new business rule. Now, if one of the orders was empty, still we apply the filter to the other one. If both orders pass, we return both orders. If none of the orders pass, we return empty container. So in this way, we have implemented these business requirements. But now I would like to ask, well, I can come up with any number of other requirements of this kind. Which of them actually make sense in terms of filtering? And this cannot be answered without some mathematical principles or laws that allow us to decide whether a certain function satisfies the laws and therefore it makes sense to be used as a filter. Otherwise, we're just going to argue opinions, and that is not productive. So what are these mathematical laws? In order to arrive at them, we need some more intuition, and now we can generalize from examples we have seen. The main intuition here is that computations in the functor block should be reasonable. They should make sense. In other words, here's a functor block program. This program should make sense. You should look at it and reason about it in a way that is intuitively correct, mathematically reasonable. So let us now think about it and derive what these mathematical requirements must be. So here's a kind of schematic example of a functor block program. The first line must be the line with a left arrow, which let's say has some functor on the right hand side, let's say list. So then the entire block will be computations, as we say, lifted into the list functor, or computation in the context of the list functor, which means that we have some data here, and we're going to manipulate this data, and the results are going to stay as a list container. Now let me go back a little bit and remind you that this is not modifying the container in place in any way. These are mathematical computations. They're not modifications of anything. These are values. So from the point of view of the program, this was one container, and the result of this expression will be another container, while this original container is left unmodified. So this is just a mathematical kind of computation, which, if we look at the mathematical equation like this, we don't say, oh, was this x modified? Was this x modified when we did the cosine x? Was this x replaced by cosine x in any way? No, it wasn't. Mathematically, we never talk about that. We never do this, replacing a value. Values are values. You cannot replace 100 by anything. It makes no sense. And so let's not replace anything. We just compute values. So similarly here, we just compute new values every time. Now, imagine we have some kind of program like this. We compute some functions, we filter on some conditions, we again compute some more functions, again filter on some more conditions, and finally we get some function of all these, depending on all these values we computed, and all these values computed here will be put into the final list. And all the values that did not pass any of these tests will not be put into the final list. So what do we expect to be true, intuitively true, about such programs? Well, one thing, for example, here, we have a condition depending on y. But y is defined as f of x. So if we put this f of x here instead of y, we should be computing the same thing. It's the same condition. X goes over all elements in this list, then y is computed, and then we check some condition. We should be able to get the same result if we check this condition directly on f of x instead of y. And we should be able to do it first. So the order should not matter then. Once we write if p1 of f of x on this line instead of this, and then we write this on the next line instead of that, so we interchange these lines and replace y by f of x, that should be exactly the same thing, because these are values that we computed and these are conditions we evaluate. If that were not true, if somehow Scala compiled this to a different code, it would be highly confusing. You would not be able to simplify your program by substituting values into other places. You see, it looks like y is equal to f of x, but then somehow you cannot substitute f of x here. That would be highly confusing. Or you cannot first compute f of x in the condition, and maybe you don't need y then. Maybe all the rest doesn't really need y. You can simplify your program. So you want to be able to do that, to reason about your program like this. Here's my value. Let's substitute it in here instead. Maybe the program becomes simpler. Now, it means we have this requirement. Any program that has this kind of code must be equivalent to any program that has this kind of code. Notice the semicolons I put them here because Scala also allows you that syntax. You can put this entire functor block on one line if you wish, and separate the lines with semicolons. But this might be harder to read. It's up to you how to write the code with one line or with many lines. The next requirement is found if we look at these two conditions. Intuitively, first we check P1, and we only pass those values that satisfy that first condition. And then we check the second condition, and from those that pass the first condition, we additionally take only those that pass the second condition. So that should be equivalent to checking just one condition, that is the conjunction of these two conditions. That gives us the second requirement. The third requirement is somewhat trivial. If a predicate always returns true for all values of x, for instance, if this P1 were just identically true, then we should be able to remove this check from the program, because that should not affect at all what's happening if we remove it. All the values will always pass to the next line, and so that's the same as if this check wasn't there. So that's our requirement 3. Another final requirement, quite important in fact, is that remember what we had in our initial computation, that the filter was for positive y, and then we took the square root of y. Now if some y were negative, we shouldn't be doing square root of it. So in other words, we rely on the fact that only values that pass the filter will ever be used in further calculations after this if line. Just like we rely on this here with after the filter, we rely on the fact that data that do not pass the filter will be omitted from any further calculation. And so we formulate that as a requirement that whenever a filter predicate p of x returns false for some value of x, then that value of x will not be included in any computations performed after that line. So that is our final condition. So these are the 4 properties that functor block programs must satisfy. Let us now formulate these properties mathematically. In fact, it is very important that we can formulate these laws mathematically. It's not just talking about the program, what you could change in the program without changing its result. It's not just words. We can actually write equations and check them to see that these conditions hold. How do we do that? For instance, we write the first law like this. We say, whenever there is a function f and a filter condition p, such as here, the function f and the filter condition p, then we look at how this part of the functor block program will be translated by Scala compiler into the map and filter. So this will be map f filter p, and this will be filter p of f map f. In other words, this will be compositions of the functions map f. Here I say f map because that's the right type, the flipped map. Its argument is f. So map f composed with filter p must be equal to filter of f composed with p, which is this. Remind you that function composition works from left to right when you write it with this symbol, f composed p. But if you want to write it specifically as code, you must put the functions in the opposite order, p of f, because first you took f of x and then you applied p to the result. And so that's first you took f and then you applied p. In Scala there is an operation called and then on functions, which does exactly this. So in Scala this code would be f and then p, which is a nice and visual way of writing function composition. Notice here, I did not write it here because this is actually going to be code, but I could have written elsewhere. And I will be writing this in the example code. I will be using and then. So, in other words, the functor block program that has first a map step and then a filter step is equivalent to the functor block program that first has a filter step with a different condition as it is necessary, as we were thinking here, and then it has the map step. Now, what does it mean to have one step of a functor block program? Remember how the functor block program is translated into maps and filters. Each line actually is replaced by a step. So a function, map, or map with a function, filter with a function, and so on. So instead of saying the functor block program remains the same when we do this and that with the line, we say the map with this function would do the same with the functor value as a map with another function times filter with another function, and so on. So we actually say, instead of saying the functor block program remains the same when we change the number of lines or something, we say the functor value itself, the value of the sequence or the value of some other functor, the functor value itself is transformed in the same way by a certain map and filter operation. And that's what it is. So fmapf is a function that transforms the functor value into another functor value. The filter p is a function that transforms a functor value into another functor value. And so this law says that functor values are transformed in the same way. Any functor value, whatever you want, will be transformed in the same way by these two functions composed and also by these two functions composed. If this is so, then you can replace here this map filter with that filter map. And for any functor value here, and this could be actually a long functor program before that, so this could be, instead of just a simple sequence, this could be sequence.map.map.filter.filter.map, all inside this expression. Regardless of this, the transformation by these two functions will be the same as the transformation by these two functions. So it is in this way that we can stop talking about just replacing lines in code and start talking about mathematical functions and their equality. That has a great advantage because, first of all, functions have types. We can check that types are correct. We can reason about functions with types much better. Second, functions have values that we can check to be equal for all values of the argument. This is what we have done before with the functor laws. And we will do the same now with the filter laws. So this was the first law. The second law represents this condition, the conjunction law. By the way, laws have names for convenience, but actually they're just equations. So the first law is called naturality. This comes from category theory, and it's not important why it's called naturality. But basically, whatever law you have that interchanges your interesting function with fmap or map, that's naturality. So typically that means you can map the contents of your container before your operation, or you can map it after your operation, and it's equivalent in some way. So that's naturality. Naturality expresses the idea that you're manipulating data inside the functor in some way or inside a container. And this manipulation preserves the data items. It does not look into their details. So when you map the data items from one type to another, then your manipulation would be equivalent to some similar manipulation followed by the transformation of the data items. So, for instance, if the manipulation is to omit some elements, then you can omit them before transformation, or you can omit them, sorry, this will be after, you can omit them before the transformation, or you can omit them after the transformation. If the condition is adjusted appropriately, the result will be the same. Or this could be a transformation that somehow rearranges the order of elements or does some other such thing that does not actually look into the elements' values themselves, but just rearranges something about them. It can omit them, it can duplicate them, and so on. So all these transformations are called natural. And so therefore this law of naturality is called. Let's look at the second law now. The second law represents this requirement that if we have two conditions next to each other, then we can replace them by a single condition that is the conjunction of these two. Mathematically, we can say that the filter transformation, so think about filter P as a single symbol, just like fmap f is a single value that transforms the functor values fa to fb. So filter P transforms fa to fa. So this is a transformation fa to fa composed with another transformation of fa to fa. And they must be equivalent to a filter transformation, again fa to fa, when the predicate is equal to the conjunction of these two predicates. So I have written down the mathematical conjunction, but of course in Scala code it will be just the double ampersand Boolean conjunction. So that's the second law. The third law is that if the condition is identically true, it returns true for all x, then the transformation that the filter makes on the functor is identity. It does not change the functor value at all. And if this is so, then whenever you have a filter with identity function, you know that whatever was before is going to be identically preserved by that kind of filter. So you can just delete that operation. And that would correspond here to deleting this line, if this were an identically true condition. So in this way you see how mathematical laws actually represent the general way of manipulating code. And the fourth law is a little more complicated to formulate. So filter P and followed by some map that's we're trying to describe what it means that X will be excluded from computations performed after this if. So we need to put some computation after this if. Let's say this is a computation that is transforming by f. It could be a filter, right? So we have filter or fmap as possible computations, but we already have a law for what happens when we have a filter followed by a filter. So now we have a law about what happens when we have a filter followed by fmap. So this computation f should not see any values x for which p will return false. How do we express that f should not see those values? A good way to express that is to use a partial function instead of f. I denoted it like this. So f bar p is a partial function that is only defined for those x for which the condition p holds. In Scala, this could be written like this. It's a case expression with a condition, and if the condition is true, we just return f of x. So we don't change the function f. But now, if the condition is not true, this partial function fails. It will be a runtime exception if we apply this partial function to a value x for which p of x does not hold. So the filter guarantees, however, that all further computations will never see such x for which p of x does not hold. And so therefore, it should be safe for us to use that partial function here after the filter. So the filter transforms fa to fa. Look at this type signature again. Filter p, so we put the first argument, and the result is a function from fa to fa. So filter will transform fa in such a way that the values that are left in it will always pass the condition p. And so it is safe to apply a partial function. Not only it is safe, but it will give the same result, because the partial function is made out of the function f unmodified. So therefore, we have this law that filter followed by map should be the same as filter followed by a partial function map. And it should be safe, and it should give the same result. So that is, well, that it is safe, mathematically we don't know how to express that. We just say it needs to give the same result. If it always gives the same result for any functor values that you put into this transformation, then you are safe. So here are the four laws, and we can define a type class, let's call it filterable, and the type class will have a method with filter, which will be a partial type to value function. And this function must satisfy these laws, together with fmap. So we cannot really define filterable without also defining map for this type. So this partial type to value function must be defined in such a way that it requires already the functor type class as a constraint. So it is only defined for types for type constructors that are functors. And so then for those we already have fmap with the correct laws. So those are necessary for filter. So filter is a further property of a functor. And so we can say it's a filterable functor. So let us see if the laws hold for the functor example that we have, the orders, with Tuesday and Friday. We will also look at some examples of the functor block program notation. So before we return to the orders example, let's refresh the functor block notation. So here are some examples. We take integers from 1 to 10. We perform some calculation with them. So there's this y will be computed for each of these x's. Then we impose the condition that y is negative. And only for those y's we continue. So then z is computed, then we impose another condition on z. And then we compute something else, but actually we don't use this, p, and that's fine. And then we return a tuple. We don't actually return a tuple. We return a sequence of these tuples. The yield is not the final result of this entire functor block. The yield is the result of a single computation for a single data item inside the functor, or if you wish, the container of data. So now I will showing some transformations that you can make. So for instance, here, instead of saying if z is less than 100 on line 86, I'm saying on line 96 if this entire expression is less than 100. And then I compute z later. And that gives the same result. And also, instead of doing p equals z minus x, which I'm not actually using, so I should actually delete this from the code. I use p here, and that's exactly the same. So you can put more computations into the yield part of the block, or fewer computations, you can put some of them here. It's entirely equivalent, and the only consideration here is readability. How easy it is to read the code and understand what it should do. Also, I can mathematically express this condition as a condition on y, as that absolute value of y must be less than the square root of 100 minus x. And again, it gives the same result. So I can transform these conditions in any way I want, and the results are the same. And finally, I merge these two conditions for y into one condition using the conjunction law. And again, the results are the same. So this is the test that verifies that. So this is the way that we expect the program to behave. We expect to be able to simplify the program in certain ways, so that, for instance, here we notice we compute this expression twice. Let's not do it. Let's compute it here first as z and then use it. That's a typical transformation of a program that a programmer would do. So we see that the naturality law, the first law of filter, guarantees that this program transformation is valid. It does not change the result. What a surprise it would be if that were not true. A programmer would look for a bug for a very long time. And this is because reasoning about the program has become broken if you break the laws of the filter. So it becomes impossible to reason about the program by looking at the code. We should avoid that at all costs. Breaking mathematical laws is something that has real costs, that has real consequences. Makes our life much harder. So now let's see if these laws hold for the orders example. To do that, we define the type class instance. In the example code, I have defined type class called Filterable with filter. I have not found a standard filterable type class in libraries, either in the cats or in the Scala Z library. So I defined my own. It's just a few lines of code to do that. We'll see how that is defined. It's using an abstract class with an implicit functor value, which means that you cannot create instances of this abstract class without having a functor instance for your type constructor f. So in this way, I enforce that filterable here must be already a functor. And then it has this method, which is the way I implement the partial type to value function. So I define the partial type to type function and a partial type to value function. The other type class is just called filterable, not filterable with filter, and it does not define a function with filter. It defines a function called flatten. So this we'll be talking about in the second part of this tutorial. For now, we only look at filter and its properties. In order to define a type class instance for orders, so that we define a partial type to type function extending it to orders, we need to define this and override the function with filter. And also we need to have a functor instance for orders. Until we have that, this wouldn't compile. So we need to have the functor instance. Well, the functor instance for orders is a straightforward thing. Orders is a simple conjunction type, option times option. So the cats library has an extension that derives such functor instances for case classes. So I'm just going to use it. Very convenient. Very little typing. When it works. We will see cases when it doesn't work. So we first define a functor instance and then a filterable instance. So how do we define a filterable instance? We just override the function with filter in the class, and this is exactly the same code as we had in our first example. We filter the first option, we filter the second option. Now notice that this is a standard library function on options, so this is not the function I am defining. So this is not really recursive in any way. This is a standard library function already defined on an option, and a very easy one to implement. So then I check the laws. Now I have implemented this law checking helper, just as I did with functors. So let's look at how it's implemented. So it has a bunch of arbitrary values that it wants, and then for all these values it will check the laws. So the first law is that map followed by filter is the same as filter followed by map. The only thing is that the filter needs to have a different function type. So this is A to B, this is B to Boolean, and this is A to B, B to Boolean. So this entire thing is A to Boolean. So then it is filter of A and then A to B. So first you map filter, then you filter map. And that should have equal values. The conjunction law is that you do a filter.filter, and that's the same as filter with this function. The identity law is that you do a filter with something that's identically true, and that should be exactly the same as what you started with. So in all these examples, I have an arbitrary value of the functor, and I check that for an arbitrary value of the functor, these transformations are equivalent, give the same values. So for this, I need to be able to compare values of the functor. So I need this extra function, compare for equality of the functor. This is very similar to what I did in the functor type class. The final law is the partial function law, for which we say it's a filter P and then map F, and then we do a filter P, and then we map using this partial function, which is F, except that it's only defined for those x for which P of x is true. So here are the four laws. Naturality, sometimes called parametricity, but let's avoid the mumbo-jumbo. And naturality is not mumbo-jumbo because it's natural. So conjunction law, identity law, and partial function law. So this test passes, so the laws hold for this orders functor with this type class instance. Now, notice in this test, I define the functor instance outside the test, but the filterable instance inside, so that I can define different filterable instances in different tests. And that's what I will do. I will first verify example 1, which is this straightforward filtering. Here's how it works. So we can use it in the functor block notation. Data is this orders of 500 and 2000. So x is compared with 1000, which is our approval criterion, and then we transform to a string. And the result is the orders of transformed, and they're printed more nicely. And the second order was not approved. So the first order was approved. The second example is the orders with business rule A. And orders with business rule A is this more complicated code that we saw before. Again, we check the laws. And notice we define a different filterable instance. And so this checking is with a different instance. And exactly the same functor block code returns now empty orders, because for business rule A, both orders need to be approved for any of them to be placed. And so exactly the same functor block code now gives a different result because we define the filterable instance differently. And interestingly, the example 2b does not work. It breaks the functor law. Sorry, the filterable law. It does not break the functor law, it's still functor. It breaks the filterable law. And so this fails, and actually there is specific data that shows it to fail. Also, it fails the partial function law. And so we will look at it why that happens. For now, let's look at this. Well, actually, let's finish with the orders. Why does the law break? It's an interesting consideration. So if we filter with one filter and then with another filter, that should be equal to the filtering with a conjunction. Now, in this example, I chose these two conditions so that their conjunction always returns false. So we should be having an empty container after this. However, in the data, one of the orders is below and one is above 1000. And so the business rule 2b says that both orders can be placed if at least one can be approved. And so then, after the first filter, both orders are still placed. And after the second filter, also both orders can be placed. However, if we filter with the condition that no orders pass, then we get an empty order. So that's not the same. And also it breaks the partial function law. We filter with a condition, and we use a function that is only defined when that condition holds, and we have an exception at runtime. So what happens here is that it's counterintuitive. We thought we would limit computations to these x, but actually we have not limited them to that x. The 2000 is still there. So reasoning about a program that uses this filter implementation would break our intuition about what filters should do. And that's why this is not a good filterable implementation. So business rule 2b is not filterable. So now consider the example of this functor. It is a disjunction that has either no data items or two data items. So it's a product or nothing. How can we implement it as filterable? So I call this a collapsible product for reasons we will see momentarily. Well, we first derive a functor for it. So the type is just an option of tuple AA, which is this type. Now, how do we define filter for it? Well, let's write this function. So we have fa of type option tuple AA, and we have a filter function. So now option tuple AA has two cases in the disjunction. First is that it's non-empty with some values x and y. Now what can we do? We must apply the filter to both of them, because if we don't, we'll fail some of the laws, as we just saw with the business rule 2b example. When we don't apply the filter to some of the values, then partial functions will fail, and conjunctions may also fail. So now, if we apply to x and we also apply to y, what if one of them passes and the other does not? Well, we have to exclude the one that did not pass. But our type has a disjunction that has only two parts. One must have two, and the other is empty. So if x passes and y does not pass, we cannot retain y. We could retain x if we had any way of retaining x, but we need two values. So we cannot just put x here, we need another value. We could put x twice. I'm not sure that would be a good idea, though. It doesn't feel right. It probably will violate some law if you do that. It feels wrong that you duplicate values. It would be, I have not checked it, so you're welcome to check if the laws hold with that implementation. But the most reasonable implementation is that if none of them, if only one of them passes, we need to remove both. So we get the empty container. So that's how it's implemented. So only if both x and y passes the test, the container is unchanged. I just write fa just to save typing sum of x, y again, and it's faster. Otherwise, we return empty container. So laws hold. I checked the laws with different types, just to be sure. Now, as a reminder, this function takes type parameters, so that it cannot just check laws with all types at once. It's impossible. You have to give specific types on which you would check the laws. So, transform from int to string to something that need to be specified. So Let's look now at examples of functors that are not filterable. So we have seen that orders with business rule B will break laws. It actually breaks law 4 as well. Now, another example of a function that is not filterable is a function that defines filter in a special way for certain types. For example, for integer type, it defines the filter function in one way, and for all other types in a different way. So that is not natural. The filter should not look at types. It should manipulate data without regard of its type. So this type A should be unknown type, and it should not check that it is integer or something else. So it actually breaks law 1. So let's look at how that works. So here is this functor, A0, which is just an option. And I'm going to define a filterable instance where I define a filter, not in the way that usual option is defining the filter. I will first check if the type is integer. If the type is integer, then I'm going to check the condition. If the condition passes, I do what was before. I return the same value. If the condition does not pass, then I return 0. So this is actually 0. So I specially prepared this. So if the type is integer and the filter fails, I replace the integer by 0. That's a special rule that's only used for integer. For all other types, I do the standard thing and filter on an option in a standard way. So this kind of thing is an incorrect implementation of filter because it is not natural in the type. It is using some information about the type that is not parametric. And what happens is that as long as you don't try to use the integer type, then you are in this second case, and it's all right. It's correct. But once you start using the integer type, then naturality law fails, and if you uncomment this test and run it, it will tell you that it failed in the naturality law. And here's a counterexample that breaks naturality law. We say this data is sum 0, subtract 1, and check that it is greater than 0. And another way is to check first that x minus 1 is greater than 0, which is the same, right? Y is equal to x minus 1. So I could put this x minus 1 in here, which I did, and put the condition first, and that should be the same. It doesn't matter if I first check the condition and then compute x minus 1, or if I first compute x minus 1 and then check the same condition. But the results are not the same. So actually, the first result is not equal to the second one. The second result is not empty. The first result is empty. So that is a clear violation of the naturality law. So this shows you that we're trying to reason about the program, and we refactored the program in some way, and the results changed. This kind of bug would be very hard to find. You refactor your program and results change. Another example is this functor, 1 plus a, where the filter is defined so that it always returns 1 plus 0. Now 1 plus 0 is my short notation for this part of the disjunction, so it's only the unit. So 1 plus a is option of a, and 1 plus 0 would mean none, so you always return none part of the disjunction. Now, if you do that, here's our implementation. So the filter always returns none. That breaks the identity law. You filter with true, and it's not the same, because it always returns none. So if you did not have none to begin with, you get none, and that's regardless of what you filter. So even if you filter with a true, that's still none. So that breaks the identity law, the law 3. So these are, so far, wrong implementations of filter. This is an option type, as we know. It has a good implementation of filter. So now the last two examples are functors that cannot have an implementation of filter. They are not filterable. So let's see how that works. The first is the identity functor. It's not filterable. Identity functor needs to implement filter, but how can we implement filter? Well, we get a value a, and we need to return, let me just rename this to a for clarity. We get a value of type a, and we need to filter. Now, if the condition does not pass, there's nothing for us to do except still to return the same value. So we cannot actually apply the filter. There's nothing we could do. If the filter were to return false, there's nothing we can do. We must return a value of type A. And so we return the identity. So basically, this is a filter that always returns identity. It does not ever filter out anything. And that breaks the partial function law, because it does not filter out anything. And so we rely on filtering out certain values, and that expectation is broken. So here's an example. We have some data with a negative number. We filter by positive, we take square roots, and we expect that everything is fine, but actually the result is this, not a number, because square root of a negative number is not a number. And so our expectation is broken. And the second example is this functor. It's a product of a and 1 plus a. Now 1 plus a is option, a is the identity functor. So it's a product of two functors. One of them is not filterable, we just saw. The other is filterable. It turns out that the product is still not filterable. So why is that? Well, a very similar reason. We have a value of type t and the value of type option t. If this value does not pass the filter, we need to remove it somehow from the container, but we can't. The container always must have a value here. It's a product, so it requires both parts. And so it always must have a value of type t here. We cannot remove it. So let's suppose this were some value and this were an empty option. So this were none. The only way we could filter this is to retain this value x. And that's the same problem as we had with the identity functor. If we do not filter out values that don't pass the test, then we violate the partial function law. So this is exactly the same test as before. We violate the partial function law. So to summarize this, these laws 1 to 4, these are equational laws. In other words, these are equations for functions. They're not just some kind of vague descriptions of what we do with the code. These are actually mathematical equations for functions that can be proved to hold or not to hold. And these equations rigorously specify what it means to filter data in the container. So we have derived these 4 equations from our intuitions about what a filter should do. Now we will only use these equations. We will not need to do any more intuitive reasoning. We're now on solid ground, and we will derive various functors, filterable or not filterable, in these worked examples. In the first example, John has up to 3 coupons and Jill up to 2 coupons. All of John's coupons must be valid, but each of Jill's coupons is going to be checked independently. Why is this even described by a functor? We need to abstract the problem from details and see how we can represent this as a functor. And then we will see what is the filterable functor. First of all, to represent this as a functor, we need to have a type constructor. So what is a type parameter? Well, clearly the type of coupons. The functor is going to be the container with all the coupons. The type of the data that coupons represent is going to be a parameter. So we're going to abstract away a specific type of the coupon data. So then we have a container that has 2 parts. So it's a conjunction. The one part is John's coupons, another part is Jill's coupons. And the first part will be itself a disjunction, because it can have 0, 1, 2, or 3 coupons. The second part, 0, 1, or 2. So once we reformulate the situation in this way, it is clear that it is represented by a functor. And then the conditions of coupon being valid is an arbitrary condition, which is a predicate, a function from coupon type to Boolean. And we're going to filter our container using that condition, and the result will be a container having all valid coupons, according to the logic defined here. So the first thing I would do is to write the type in a short notation. Then I can have a bird's eye view of the data. So the type is a conjunction of 2 parts. John's coupons is a disjunction of unit, 1 coupon, 2 coupons, 3 coupons. And each coupon is represented by a data item of type A. Jill's coupons is a disjunction of 0 coupons, 1 coupon, and 2 coupons. So now we can implement this in a standard way using sealed traits and case classes. So for convenience, we first implement the left part of the disjunction and the right part of the disjunction, of the conjunction. And so at the end we'll have the functor coupons, which is the conjunction of John's coupons and Jill's coupons. As before, we need to define the functor instance, so we use automatic derivation for functor instance. Now it remains to implement the filterable. So the logic is that, first of all, John's coupons and Jill's coupons are validated independently. So John's are independent from Jill's. For John there is one kind of logic, and for Jill there is another kind of logic. So what is it for John's? Well, if there is any number of coupons, there could be none, and then we don't have to filter anything. If there's any number of coupons, then all of them must be valid by the filter condition, and then we retain them, otherwise we discard them. So The logic is that if John has no coupons, then we return again the no coupon situation. If there's one coupon and the condition is valid, then the coupon is retained. Otherwise, we return the empty situation. If there are two coupons, then both must be valid, and then we retain both of them. Otherwise, we return the empty situation again. And similarly, for three coupons. So that's the logic for John's coupons. And for Jill's coupons, the logic is just examine each coupon separately. So if there's one, we keep one. If there are two, we see which one returns true. So we use this matching on the pair. So we compute a pair of two Boolean values corresponding to whether the filter results are true or false for C1 and C2, which are the two coupons of Jill's. And then we match at the same time on both values of the pair. So that makes the code a little more clear and readable. So we have just 4 situations, and we return 1 coupon or 2 coupons or 0 coupons. So finally, having computed the new filtered John's coupons and filtered Jill's coupons, we put them into the coupons case class, into the conjunction. And that's our result. So now here is some test data. There are 2 coupons, each for John and Jill, but the condition is that the value must be above 150. And so for John, one of them is below, and so none of his coupons are valid. For Jill, one of the coupons is valid, and then this functor block will transform the coupon value into a string. And so we see that John's coupons are all gone, they are not valid, because one of them is not valid. But Jill's coupons have been filtered differently, so the valid coupon is retained, and there's a Jill1 disjunction part. So that's how we can implement this situation, and this is indeed a filterable functor, which we can check automatically by the helper function that checks the laws. The second example is that we imagine that there's a server that receives a sequence of requests, and each request must be authenticated. Now, there's a special logic that once a non-authenticated request is found, the server accepts no further requests. How shall we describe this with a functor, and how shall we make that functor filterable, if possible? So the server is representing a sequence of requests. So let's first of all generalize the request type to R. So we have then a sequence of R as requests. We make the functor instance for the server, and that doesn't seem to work with the automatic generation, so we just do the map by hand. This is not a lot of code. The server is just a sequence wrapped in a case class, so we just need to call map on the sequence. So how do we implement filterable? So we need to take requests one by one until we find a request that is not authenticated. So we abstract the condition for being authenticated as a predicate that goes from A to Boolean. And then we use the function takeWhile, which is the standard library function defined on sequences. And this will take the initial part of the sequence until while the predicate is true, on the elements of the sequence until we find an element that fails the predicate, or until the sequence is over. So we compute that sequence, and so we have the resulting instance. Testing this, we do using this test data. So let's say the condition for acceptance would be that the square of the number is less than 1,000. And so then only the first three numbers satisfy. Now I could actually put a 0 here, and it still would just be the first three, because after this the take while will stop taking elements once one element was found to fail the condition. And so this logic is now encapsulated by this code. You see, in this code I do not mention this logic that the server should take sequence and so on. It looks like I am just processing elements one by one. For each x in the container, compute this and check this condition and then compute this. So this code describes what I compute, and the logic about how elements are retained or emitted from the container is encapsulated in the filterable instance that we defined over there. And as usual, we check the laws of the filterable. The other examples already start with a data type. In the first two examples, I showed how you can take a real-world situation and convert it into a functor with a filterable instance. So this should help us learn to recognize such situations in real life and make code so that the logic of filtering is separate from the logic of checking data for conditions. And so the filterable instance helps us separate such situations in three parts. First part is the data type, for which is completely free. It's data. It's a type parameter. So we completely separate all knowledge about the data type into a different part of the code. Second is the predicate on which we filter, so the specific logic for checking valid coupons or authenticating requests. So that's a function from this data type to Boolean. So again, this is implemented in a different part of the code. And the third part into which we split the code is the filtering logic, which is which elements are retained and which elements are emitted under what condition. So the condition is already given, but then, for instance, for John, all coupons must be valid, or for Jill, they're all independent, and for the server, the initial subsequence must be all valid, and so on. So that logic is what the filterable instance implements. And so by recognizing these situations and structuring the code in this way, we separate concerns. And so in the following examples, we assume that the first two logical steps have been made and we already have a data type, and it only remains to see if that data type is filterable, and if so, to implement the filterable instance. The first example is this case class, which is written here. So the first step for me would be to write this in a short notation, because then I can see much more clearly how to implement anything with it. So the short notation would be this. So there's an option and a conjunction or product with an option of tuple. So now I look at this type and I see it's a product. So I can filter this because this is an option, and I can filter this because we just had this example. This was the collapsing product example. I can filter both of them, so most likely I can easily filter the product by just filtering the two parts. So let's see how that works by actually declaring separately the filterable instances for the two parts of the product and then combining them. So the first type would be option A, and the second would be option of tuple AA. So that's the first type, the first part of the conjunction, and the second part of the conjunction. So the functor instance needs to be defined, so we use the derive for that. And the filterable instance needs to be defined, so we define these functions in the usual way. So I just wrote out here the code, which would be exactly the same as fa.filterp. But just for clarity and to illustrate what exactly it is doing, this is the code. So the option, the standard filter instance for option, if it's non-empty, we need to check the condition for the value that's in it. And if the condition holds, then we return the non-empty option as it was, so unchanged. In all other cases, either it was empty or it is not empty but the predicate does not hold, we return empty option, none. The second functor is the option of a tuple. And here we did what we did before. If both conditions are valid, we return unchanged, otherwise we return none. So either we had an empty option here, or we had a non-empty option, but one of these conditions failed, so then we return empty option. So now we have defined two filterable instances for the two parts of the conjunction. Let's now define the filterable instance for the conjunction itself. So this is this class P that is defined here. And all we need to do, so again we derive the functor automatically. All we need to do really is to take the two parts of the conjunction and filter them separately. Now, just to note this detail, that the syntax, the dot filter, is available because of this type class. So the first is of type f1 of a, so it's some kind of functor. Second is of type f2 of a, that's another kind of functor that we defined. These functors do not by themselves automatically get a dot filter method. So this method as a syntax appears once you define the class, the type class of filterable, and then in the imports at the top of this test file, if you look at the imports, I have import filterable. So the filterable is the object, filterable underscore. So the filterable is the object that contains all the syntax for the functor, for the filterable type class. So this is the way that it is defined, which we already saw in the previous tutorial. So let me just go very quickly over it. The filter syntax is defined when we have already with filter. Then we define also a filter as an alias to with filter. And we also define other functions, which I will talk about later. But this is this implicit class that converts your functor into something that has this syntax. This is a pure syntax extension, which does not change the code. We could have used a different syntax. We could have said, get the evidence value for this partial function, and the evidence value contains the filter, call that, and so on. That would be just less readable. Using that syntax, we have this more readable style of dot something, dot something, dot something, which is easier to read. So now we can check the laws for the P using these definitions. So you see it's very easy to derive filter instances from parts that already have filter instances, and we will look at it in more detail later. The next example is this type. Now, if you look at this type, it's int and int here and also int. So each part of the disjunction has an int. So we could factorize int out like in ordinary algebra with types. And we have int times 1 plus a plus aa plus aaa. We could have done this like that. And then we already have a filterable instance for this type, because this is John's coupons in the previous examples. We already have an implementation of this type, so we could just leave the integer unchanged under filter, filter this, and we're done. Now that implementation is possible and valid. There's another implementation that's perhaps more interesting, because it keeps information about what items were filtered out. And it gives you non-trivial information in these integer values. And yet it is still consistent with the laws. So let's see what we want to do. Well, so let's look at this type that we're given. Suppose that we are in this part of the disjunction. So we are given a value which is in this part of the disjunction. Then we filter something, and we have one of the data items not passing the test. So two of them are left. Well, clearly we have an int, we have two data items, so we should be in this part of the disjunction. So we will move data over here, and in this way we implement the filter. That's how we did in the Jones example, Jones coupons. But we can also add 1 to the integer value here to show that we have omitted one data item. So more generally, this type allows us to implement a filter in such a way that whenever we omit some data items, we can add the number of these items to the integer value. And in this way, we will, in some sense, keep track of how much we have lost. So how many have been filtered out. This could be an interesting implementation for certain cases, maybe. So let's see how it works. So we implement, first of all, this type as a sealed trait with 4 case classes. So it's a disjunction with 4 parts. So this part will be just the integer. This part has 1 item, 2 items, 3 items. Implement the functor instance. Now we implement the filter instance. So how we do this? Well, actually, this is a bit complicated because of all the different cases that can happen. So in order to simplify the code, I implemented a function from list that converts a list of A into this data structure. And a list of A should be at most length 3. This function takes an integer and takes a list of A, and then it finds out how many elements are in the list. And notice this thing, it adds to the integer the number corresponding to how many elements were not in the list. So now I'm using this function and implement the filter. So if I have 0 elements, I return 0 elements, nothing to filter. If I have 1 element, I check the condition, and if it passes, I return unchanged. Otherwise, I return the 0 elements, but I increment the n, showing that I have omitted 1 element. And similarly, for all the other cases, I filter, but then I put the new integer into the data items. In other words, that's what I implemented. So here's an example. So I have initially 3 elements with integer equal to 0. Then I have a condition that the string has length less than 4. Only 1 element passes that test. And so this code will give me a list of 1, L1, with a value Firefox, and the integer value 2. So that was here, so L plus 2, N plus 2. In other words, I know that after filtering, this is the result, the Firefox, and 2 items were filtered out. So in this way, I can implement more interesting logic and keeping track of how many items were deleted because I have the integer value in the types. So that's an interesting implementation of the filter. And I can, of course, I should check that laws hold. In fact, if I changed anything here, if I put n plus 3 here, for example, instead of n plus 1, the laws would not hold. Why is that? Because, for example, we have a conjunction law. If we filter by one condition and then filter by another condition, the result must be equal to the filtering by conjunction of the conditions. So the keeping track of how many elements were deleted must be consistent. It must actually keep track of the number of elements deleted, because only that will satisfy the conjunction law. If you first delete 1 element and then you delete 2 more elements, then it should be the same as if you deleted 3 elements right away. And so the integer must reflect that. So if the integer does not reflect that, you will violate one of the laws. The next example is the functor, which is non-empty list. It's a recursive functor defined like this. So it's type f is defined as a disjunction of a or a times f. And so it can be A, or it can be A times A, or it can be A times A times A, and so on. So it's a list that has always at least one element. It's just like a list, except it does not have the unit. It cannot be empty. So actually, this cannot be filterable. The intuitive reason for this is that the empty container cannot be represented. So this disjunction has this form: A plus A times A plus A times A times A, and so on. And all the parts of the disjunction have at least one item of type A. And so if, let's say, the filter condition were identically false, we should have excluded all data items, but we cannot, because there is no part of the disjunction that represent no data items. There must be at least one somewhere. So if we had a functor like this, defined recursively like this, or in some other way, with a 1 plus something. So if we had the unit as one part of the disjunction, then we would be able to represent the empty container using that part of the disjunction. But now we can't. So let's see how that works. So we can certainly write down the functor. A functor instance is fine. And we can try defining a filterable instance, but we will fail the laws. And the reason is, when we do this case, so how do we define the recursive, first of all? How do we define the recursive filterable instance? We use this function with filter recursively. So there are two cases for the disjunction. One case is the 1. In this case, we just have no choice except to return the same value, because there's no way to represent anything else. We cannot represent empty. Now the recursive case with tail, we don't do anything with the head because, well, we could actually. It wouldn't help us, but we could. We could actually filter the head. It's not true that there's no way to apply the filter to head. Let's apply it. It will still fail, of course, because this one is wrong. We should have used the filter here as well, but we can't. There's no way to represent the absence of data. But let's try as hard as we can. So what do we do with the head? Well, we need to check whether the predicate is true on the head. If so, then we can return this. Otherwise, what if the predicate is wrong, is false on the head? Well, we don't have this A, so we omit it. We still have f of A. We can filter f of A. Notice we are returning this part after filter. So we omit that, and we return f of A, which is the tail, which is of the same type, non-empty list of A. And that's fine, because it's recursive type. So this type is the same as the entire type. It's recursively the same. So we can return a value of this type, f of A, taken as a tail. So we can return tail, or we can return filtered tail. It will be of the right type. So this is the best we can do to implement filterable. But that actually won't help us. if we see what happens here, well, I'm just adjusting the test. So we could filter on this. So how would that work? This is an instance of the non-empty list with two elements, both negative, and we want to filter with a positive condition, and then we take a square root. So according to the logic of what filter should do, this should yield an empty container, because none of them should pass the test. So we should never compute any square roots in this calculation. But this is not what happens, because the filter is wrong. So the first one is filtered. So we are here, p head is false, so we are in this case. So we return the filter on recursive. So this is a recursive invocation of the same function with filter. We return the recursive invocation on this. And then we are in this case where we must return the same thing, since there's no other way to do anything. There's nothing else that we can return. So, as a result, the square root will be applied to -100. So this would be omitted, but this would not be omitted. So in other words, this filter fails to filter out some of the data. And that's why it's wrong. It's not going to satisfy laws, and it's not filterable. So in fact, it is impossible to implement the filter function correctly. It's not just that we didn't manage, it's actually impossible. In the second part of the tutorial, we will see why. The next example is this functor, which has two type parameters, but we are interested in the type parameter a. So there is a z, or there is an integer z, a, and a. So how do we filter that? Well, certainly it's a functor. It's covariant in a, but how do we filter? So in order to understand how we will filter this, I look at the type in this notation and I imagine what it would be if one of these failed the filter. Well, if no element fails the filter, I know what to do. I just return the same container. So the only question is what happens when some elements fail the filter condition. And so then, let's say this one fails, and let's say this one passes. So I have to exclude this one, but what can I return? I must return one of these two parts of the disjunction. I cannot return this part. Well, I could duplicate this value. It's probably not very interesting, but I might want to do this in some cases. I should return this, perhaps. Well, it's more logical, right? You have fewer data items after filtering. If you duplicate, then you don't represent the fact that you have fewer data items. And maybe it is better to try to represent that fact, if you can. And here we can, so we can actually return z. We had a z already. We can just return it. We don't need to change it in any way, we just return it. And so in this way, we will be representing a collapsible filter, collapsible product. So if at least one of them fails, then both will be filtered out, and we'll have this value, which we will use to represent an empty container. Now this value is not going to be just one value, like a unit value. It's some type z, and we don't know what that type is. But having that part of the disjunction will represent an empty container. It doesn't have any a's in it. It has a z in it, but that's not what we're filtering. We're filtering a's. So this is totally fine to represent an empty container. And notice we can only return the z because we already had a z in this part of the disjunction. So in this part, we already had a z. If we didn't, for instance, if we had this type, then there's no way for us to return a z when these two fail the test. We have an int, we have an a, but we need to return a z. We can't. And so this functor is not filterable with respect to a. So just to show you that it's important that in this functor there is a z here and a z here. Alright, let's implement. So we will just write it short without, we don't need to have sealed traits here, just write an either of z and this conjunction or the product or the tuple, same thing. So either of z and tuple of these things is the type. Now we have a type constructor with two parameters, and we only are interested in a functor with respect to one parameter. So we need to use the type lambda, or anonymous type function, which is written like this. I'm using the projector plugin, the kind projector plugin. So this syntax means take this type constructor, fix z, consider the second type parameter as unknown, and the result is a type constructor, which still waits for the type parameter to be given, and that's our type constructor. So that's the syntax. Equivalent syntax is, let's say, we could say lambda x going to f of zx. So the capital lambda introduces a type function, and so the type function is taking the type x and returning this type. So this type function is an anonymous type expression, that is unnamed type expression. It represents a type function, a function at type level. It takes one type argument and returns a type. So just like anonymous functions are called lambdas, anonymous type functions are called type lambdas. What the type lambda represents would be something like this, if we could write it, which we cannot. For example, q of x equals f of zx. Now, if z were not a type parameter, but a type that is already fixed somewhere, we could write this. And then q would be a type function that we want. But in this situation, we cannot write that because z is not a fixed type. Z is a type parameter. So we must put z here, which defeats the purpose. We want a type constructor with a single type parameter. We want to fix the z type parameter in f, and we want the result to be a type constructor with a single yet undetermined type parameter. So that's what type lambda does. So this syntax does not work. An alternative, faster syntax for this is that. So this is alternative syntax that works. And let me just, for reference, show what it would be in ordinary functions. So we had an ordinary function, let's say f of zx. We want to define a function that fixes the value of z and only considers x as an argument. So we want a function with one argument, which is f of zx. But we don't have a z to do that. Z is not available in this scope, so we cannot do that. So instead we write an anonymous function, such as x going to f of zx. So in an expression where z is known, this can be done. So we don't need a name q for this function. It's an anonymous function. So this is exactly equivalent, and the Scala syntax for this can be shorter. It would be like this. And so see, the syntax of the kind projector plugin was designed to resemble the ordinary Scala syntax for anonymous functions or lambdas, to give you anonymous type functions or type lambdas. So this was a digression just to explain what does it mean to have a type lambda. So we need to use the type lambdas. Unfortunately, the cat's derive library does not work with type lambdas, and so that doesn't compile. No matter, we implement it by hand. So we write a functor instance by hand, then we can use the Curry-Howard library to implement the actual map function, and that works here. So anyway, we can save typing, we should. Now the filterable instance needs to be implemented, and so let's go back to our type. So we have a disjunction. We have two parts of the disjunction. If we are in this part, there's nothing to filter because we don't have any A's. If we're in this part, we need to see if both of them pass the filter, and only in that case we return the container unchanged. Otherwise we return the z, which was this z. So let's implement this logic. If we're in the left, we just return the container unchanged. If we're in the right, we have an n, z, x, and y. If both of them pass the test, both of the x and y, which is x and y are of type A, z is of type z, and n is integer. Now we don't use the integer, we discard it if we're in the case that at least one of them fails. If we're in the case that both of them pass, then we return fa, which is the original value, unchanged. So actually, we could replace these unused variables. You see they're unused. IntelliJ underlines them with gray. We can replace them with underscores, which is a shorthand for saying that this is a pattern that we don't need to name. It should just match, and whatever is there we don't need. That's the usual way of doing this. So then we check the filterable laws with this functor, and that works. So we can put a type lambda as a type parameter. That works. However, we need to put specific types in terms of Boolean or integer or string or something. Otherwise, there's no way to run any code actually if your types are not specified. The next example is this functor, which is a disjunction of several parts, and one of them includes a list. So for the list, we're just going to use the standard filter instance, so filter function on the list. And we're not going to reinvent that or implement that in any other way. We're just interested in finding out how we could implement filter on this kind of thing. We're interested in these parts And list is already standard. We know how to filter lists. Although, of course, there are more than one way of filtering lists, but that's not the point of this exercise. So here's this functor. We define it as a sealed trait with 3 disjunction cases. So empty, have z, and have list. So there's a standard way in which we implement disjunctions in Scala. Now, unfortunately, we cannot implement functor automatically because cat's derive doesn't work with type lambdas, and Curry-Howard's implement does not work with list being a functor. It doesn't know how to do functor on list, and cannot derive it either because it's a recursive type that is not yet supported by this library. So we need to implement functor instance ourselves, which is not a lot of work. If it's empty, then it's empty, and we just, whatever should be mapped, whatever part is mapped is mapped. So as we have seen in chapter 4, functors are relatively straightforward to implement. So if you build a functor out of parts, then if you know how to implement functor for the parts, then you easily implement it for the entire type, and that's what we have here. So how do we implement filterable? Well, we have, again, to look at the type. If we're in this disjunction part or in this part, there's nothing to filter, no A's. And so we just return them unchanged. Always a good idea to return unchanged if there's nothing to filter. In this way, we could always return 1, of course, the unit, but then we would lose information. So if we are in this part of the disjunction, we don't want to lose that information when we're filtered. So we shouldn't return 1. Actually, that would violate the identity law. If we're filtered with a predicate that's identically true, we should not change the value. And so if we're in here, there's nothing to filter, and that's exactly the same as if we're filtering with something that's identically true. And so we should not change the value. So that means in all other cases except the case of have list, we should just return the unchanged value. Now, if we are in the have list case, which is that we're in this case, then obviously int should stay unchanged. Now we need to check if this A is passing the test, and we also need to use filter on this. So we filter this, we get another list, that's fine. But what if this A does not pass? Well, we cannot then return this part of the disjunction because we don't have an A to put in this part. This list could be empty, so there could be no A's in there, and in any case we can't get an A out of there always. And so there's no other choice except to return one of these two parts of the disjunction. But which one? Well, we can't really return z because we don't have a value of z. And z is a type parameter, so we don't know where to get such a value. But we can return 1, the unit. Well, in this case, it's a named unit. It has a name empty. But since it's a unit, we can always return it. And so that's what we do. If that condition holds, we return the have list case with filtered list here. Otherwise, we return empty case. There's no other choice. And that works. The laws pass. So all the tests here are run and they all pass. The laws are always checked. The last example is a little advanced because it introduces a new concept, filterable contrafunctor. Now it seems a lot to introduce a new concept in an example, but it's an easy step right now. We will talk a bit more about filterable contrafunctors in the second part of this tutorial. Recall that a contrafunctor is a type constructor that has a contramap function that is like map, except that the arrow is going in the other direction. If functor represents a container, that is something that holds values of data of some type, then contrafunctor represents something that consumes values of that type. It's not a container, it's actually doesn't have any values of that type. It consumes them, it needs them, so it will consume them when given. And so a filterable contrafunctor means a container that can consume less. It can filter what it consumes, and if the consumed items do not pass the test, it will not consume them. It can consume fewer items. So here's an example of a filterable contrafunctor. We will not check laws at this point, but we will check them later. Once we find more about filterable functors, it will be quite easy to understand what a filterable contrafunctor must be. So at this point, we will not check laws for contrafunctors, for filterable contrafunctors. So here it is. I just put covariance annotations for illustrative purposes, for no particular use in the code that follows. I'm not using subtyping, but just to illustrate that this is a contrafunctor. Contrafunctors cannot be automatically derived by the CATS library, which is a shame because they're just as easy to derive as functors are. But they don't exist there, so let's use the Curry-Howard library to implement the contrafunctor instance. So the contrafunctor is called the contravariant in the CATS library, and it has the contramap function with this signature. So it's C of A to C of B, but the function is B to A, not A to B. So I'll just implement that automatically. And by the way, just to check that CATS cannot derive anything with exponential types, anything with function types. It cannot derive. So it cannot, this is a very easy functor, but cannot derive that. So not supported. Well, just for our information. The CATS derive can do case classes, polynomial types only, products and sums, but no exponentials. So the Contra Filter is the function, the contrafunctor instance, which I just called Contra Filter, now is implemented as a function with filter that has exactly the same signature as for functors. So it takes a predicate from A to Boolean, it takes old value of the functor and returns a new, contrafunctor, and returns a new value of the contrafunctor. So how do we filter the contrafunctor? Quite easily, in fact. We need to return a function. So C is a function from A to option Z. So we need to return a function from A to option Z. So that is the function we return. it takes an x of type A, and it checks whether x passes the test. If so, it lets our contrafunctor consume x. Otherwise, it does not let it consume x, and instead it returns none. None is a possible value that it can return. So that's important. That in the case that our argument does not pass the test, we have to return something, and we're not allowed to let the contrafunctor consume that value. And that's similar to the partial function law if for functors. If a value does not pass the test, we're not allowing the functor to transform this value any further. So any further processing should not happen for that value. And so for the contrafunctor, this happens right here. Contrafunctors consume values, and so they should be guaranteed not to need to consume values that don't pass the filter. That's the main intuition behind filtering the contrafunctors. And so here we defined a specific type constructor, example 8, which is C of AZ with Z equals string. We can do that with specific type. Without it, the only thing we have to do is a type lambda, C of question mark Z. So that's the only thing we have to do. But here we can, if we are willing to constrain the parameter Z to be a fixed type, then we can do it. And we are doing this here because we're about to run tests, and for tests, in any case, we need specific types. So just to run the test, I need to define the equality function that will compare two different values of contrafunctor. And since they're functions, it's not immediately easy to compare them. We need to do a for all and run the functions on some arguments. And so I also have Contra Filterable laws implemented, but this is just for later. We're not going to discuss these laws right now. So now here are some exercises for you, which are based on what we just have covered. They're very similar to the worked examples I just gave. And after you do these exercises, we will go on to the second part of the tutorial, where we will discuss the laws of functors in more detail and in more depth. We will discover why the laws are like this, how they can be simplified, and how we can reason about filterable functors in a much simpler way.